This video will provide you a basic understanding of stress and strain. And it will help you understand material properties, like elastic modulus and Poisson's ratio. We start the discussion of stress and strain using the example of a simple spring. The left end of the spring has been fixed, so it cannot move. If we apply a force to the spring by pulling on it, the spring will stretch and displace by some amount, x. The spring from a garage door requires a lot more force to stretch than the spring from a ballpoint pen. Therefore, we say the spring from the garage door is stiffer than the spring from the pen. If we plot the force versus the displacement for the pen spring, we get a straight line. The slope of this straight line is called the spring stiffness, and is denoted with the letter K. Mathematically, we express the relationship between the spring force and the displacement as F equals K times X. If we plot the force versus the displacement for the garage door spring, we also get a straight line. As we expected, the slope of this line is much greater than the slope of the line for the pen spring. We will now use these same concepts to understand stress, strain, and elastic modulus. Let's use another real-life example. This pencil and this cylindrical piece of soft rubber have the same cross-sectional area. We will apply a pulling force to both of them. When we pull on the rubber cylinder, we can relatively easily elongate it from 5 cm in length to nearly 14 cm. When we release it, the rubber cylinder returns to its original length. Try as we might, we are simply not able to pull the pencil hard enough to notice a change in its length. So, what is happening? Instead of a simple spring, let's consider a cylinder. With cross-sectional area, A, and length, L, the left end of the cylinder is held rigid in a vise. So it cannot move. If we pull on the cylinder with a force, F, the cylinder will elongate, and the right end will displace by some amount, U. We use the Greek letter sigma to symbolize stress. And we define stress as force divided by the cross-sectional area. In a similar fashion, we use the Greek letter epsilon to symbolize strain. And we define strain as the amount of displacement, U, divided by the original length. Now, if we plot the stress versus strain, we again generate a straight line. The slope of this line is the elastic modulus, and is symbolized by the letter E. The elastic modulus is also called the Young's modulus, and for many materials it defines the relationship between stress and strain. Starting from an initial length of 5 cm, we elongated the rubber cylinder by 14 cm. This creates a strain of 1.8. Strain is a dimensionless quantity, but it is usually expressed as inch per inch, or millimeter per millimeter. So we have done that here. The elastic modulus of the rubber is 1 megapascal. And the diameter of the rubber cylinder is 6 millimeters. Using this information, and the relationship between stress and strain, we can calculate that the stress in the rubber is 1.8 megapascals. We can also use the equation for stress to calculate the force that we applied to the cylinder. What about the pencil? We know that we applied at least 51 newtons of force to the pencil. And likely, we applied 2 or 3 times that amount. So let's assume 125 newtons of force was applied. Then, we can calculate that the stress in the pencil was 4.4 megapascals. The elastic modulus of the pencil is 7,200 megapascals. This information, along with the relationship between stress and strain, allows us to calculate the strain in the pencil. Recall that the strain in the rubber cylinder was 1.8. So, even though we applied much more load to the pencil, the strain in the pencil is much smaller than for the rubber cylinder. We can now use the definition of strain to calculate how much we were able to increase the length of the pencil. The pencil only stretched by 0.006 centimeters. This explains why we could not observe any change in length. When we pull on the rubber cylinder, it not only stretches along its length, the diameter of the cylinder also decreases. We can better observe this effect by pulling on a thin rubber sheet. We used a Sharpie marker to create a 2.5 cm square grid on the sheet. When we pull on this thin sheet of rubber, the squares become more and more rectangular. The phenomenon that we are observing is what is known as the Poisson effect. If we define direction 1, so that it is aligned with the direction that we are stretching the sheet, and direction 2, so that it is transverse to the direction that we are stretching the sheet, we can measure how much the squares grow or shrink in these two directions. In direction 1, the square has grown from 2.5 centimeters to 3.4 centimeters. Using the formula for strain, we can calculate the strain in direction 1 to be 0.35. In direction 2, the square has shrunk from 2.5 centimeters to 2.1 centimeters. Using the formula for strain, we can calculate the strain in direction 2 to be minus 0.16. We use the Greek letter nu to symbolize Poisson's ratio. And we define the Poisson's ratio as the strain in direction 2 divided by the strain in direction 1. For the rubber that the thin sheet was fabricated from, we calculate the Poisson ratio to be 0.46. In this video, we introduced you to the concepts of stress and strain. We introduced elastic modulus, and we explained how it relates stress and strain. You saw that starting with displacement, you can calculate strain, stress, and force. You also saw that starting with force, you can calculate stress, strain, and displacement. We introduced the phenomenon called the Poisson effect. And we defined Poisson's ratio as the strain in the transverse direction divided by the strain in the direction that we apply to displacement. You can find the elastic modulus and Poisson's ratio for specific materials in many engineering reference books. They will often look similar to this table. The properties that we will enter in 3D Experience are located in these columns.